Welcome to a new session in the ISM exercise set Business Mathematics. This time with a unit on investment valuation. Let's have a closer look at the exercise. Two companies are offered for sale. The price in both cases is 1.5 million euros. The following cash flows can be expected. Then we have company 1, 300,000 euros each at the end of each of the first 10 years, and afterwards for each year 10,000 euros per year for an indefinite time frame. Company 2, 350,000 euros each at the end of each of the first 9 years, and at the end of the 11th year a one-time payment of 400,000 euros. Our objective now? Assume an interest rate of 3% and decide whether buying is economically sensible and which company can be expected to generate the highest overall profit. So what we are basically asked here is to calculate the net present value for both companies, then decide are they positive and which of them is the largest. So to get the net present value for each of the two companies, we have three parts. Both cases we have the buying costs, the buying price of 1.5 million. And with the first one, we have the cash flows of 300,000, 10 times over the first 10 years. And the more or less perpetuate payment of 10,000 euros per year for an indefinite time frame. Then, for the second one, we have the single payments of 350,000 euros for 9 years and a one-off payment of 400,000 at the end. So we're working our way through the two companies, trying to get the net present values. So starting with the first company, I have here, as I just mentioned, first off the net present value for the single cash flows, then the net present value for the ad infinitum cash flows, then minus the buying price. So let's start with the single cash flows. What I'm doing here is just recalling that what I'm having here is more or less a discounting taking place with a specific type of pattern. So for the first period, I discount once. So I divide by 1.03 to the power of 1. The value for the second year, I discount twice. So the index here is to the power of 2. And well, instead of dividing by 1.03, 1.03 to the power of 2, 1.03 to the power of 3, and so forth, I can also imagine this as multiplying it with 1 divided by 1.03, and all of this either to the power of 1, power of 2, power of 3, power of 4. So the structure means I always have the same effect. The only thing differing with each different term is the exponent. So the exponent is first 1, then 2, then 3, then 4, then 5. Meaning I can factor out the 300,000, write this before all this, and the rest I can summarize in a sum. And that's what's been done in the first step. So here this sum starts at 1, going to 10, so I have 10 observations. This is the discount factor, more or less the part where I said it's 1 divided by the discount factor to the power of j, j being a value from 1 to 10. For the 10 periods I need to discount. Okay, so why am I doing this? Because if I take a closer look, this reminds me a bit of the finite geometric series. And that's basically what I'm going to use here to make the calculation easier. However, the geometric series requires that the series starts at 0 and that the index inside the sum is actually only the index itself, not plus or minus anything. So let's start with the first problem. I need to have the series start at 0. Well, I can just subtract 1, then it starts at 0, but then I can only go to 1 less, so meaning it needs to end at 9. That's what I've done in the step from the second to the third part. Here's the sum starts at 0, goes to 9, but then I, inside the formula, have to increase the index by 1. So here it says j plus 1. Now this plus 1 is annoying me, and I need to get rid of this as well. But here I can just consider that plus 1 means multiplying the factor with the factor to power of j with 1 divided by 1.03. So I can pull this in front of the sum sign. So here, that's the next step. I'm just pulling the 1 divided by 1.03 in front of the sum sign, having the sum itself fulfill all requirements for applying the finite geometric series, meaning it starts at 0 and the index inside is a j. So here I can then apply the formula for the finite geometric series. The only thing I need for this is first the expression below the j, below the index, that's 1 divided by 1.03, and the upper part of the sum, here being 9. Because then this simplifies to this expression 1 divided by 1.03 to the power of, and that's 9 plus 1, minus 1 divided by, and then again the expression in parentheses, 1 divided by 1.03 minus 1. This expression I enter into my calculator, giving me a net present value of these 10 cash flows of 2,559,060.85 euros. That's the first part. Then I have the ad infinitum cash flows. That's, however, much easier to calculate. Here I'm taking the 10,000 per year, and following the idea of perpetuity, I divide them by the interest rate. So I have 10,000 divided by 0.03, and that's the value when it starts. It starts at period 11, so after the first 10. So I need to discount this from period 11 to 0, so meaning I divide this by the discount factor to the power of 11. Here I just written both of them below the fraction line, because if I have a double fraction, I can also do it this way. So if I divide the 10,000 first by the interest rate, then by the discount factor, this gives me the net present value of this cash flow, and this in this context amounts to 240,807.09. Then I can just add up these two net present values, subtract the buying price of 1.5 million, giving me an overall net present value of this first company of 1,299,867.94. So that's the first part. In the second part, company 2, we have here first off the different single cash flows and then the one-off cash flow we need to consider. The single cash flows, that works similarly to what we did in the slide before. However, the only differences being here, now we have cash flows of 350,000 and only 9 of them and not 10. All the rest follows the exact same argumentation that we had in the slide before. And thereby, I will just skip to the end. We get here a net present value of 2,725,138.12. As I said, the same idea applied at before. We are trying to get our sum to look like a geometric series so that in the final step we can apply the formula for the geometric series. If you're interested in rather writing this down and doing all the stuff by hand, that's fine as well. Might take a bit more time, however, then you wouldn't have to do all the recalculations we did here with the different sums. However, this was the hardest part in this context of company 2, because with the one-off cash flow, we just have to take the value and discount this 10 times. So we divide the value, the cash flow of 400,000 by the factor 1.03 to the power of 10, giving us here a net present value of the one-off cash flow of 297,637.57. So we add up these two partial net present values, subtract the buying price of 1.5 million, and get here an overall net present value of our company 2 of 1,525,775.69 euros. Then we can just compare these two net present values. That's what we are going to do here. So that's the two net present values. And well, with a not too close look, we can directly see the net present value of company 2 is way larger than the first one. Also, they are both positive, so both are lucrative investments. However, the second one results in the larger net present value. So you should decide on company 2 because this yields the larger value. And well, this then concludes this exercise. I hope you enjoyed listening to it. You could take something away from it. And if you want to see more of these type of exercises, feel free to visit the rest of this exercise set or the corresponding playlist. I say goodbye and see you next time.